Hello everyone, I'm a PhD student at the University of Bergen, and today I will present a work which we focused on studying logic formalism and learnability of this logic formalism. It's called possibilistic logic. This is a joint work with my supervisor, that is Ozaki. So we would like to, in this work, we would like to learn from imprecise, incomplete, and contradictory information, like imagine learning from unreliable or imprecise sensors, or data that has incomplete values, or also contradictory statements. And in literature, many people have studied learning of logic theories, but most of the works are on classical logics. And this means that there are, so classical logic is too robust in modeling learning scenarios in this try to, in which we have a high degree of uncertainty. So we propose to study learnability of possibilistic logic. That is a logic formalism that is able to cope with some phases of uncertainties, and I will explain later uh, what and how we can model with this logic. But first of all, I think it's useful to define um, generally what is possibilistic logic. Is weighted logic, and we define it by starting from a classical logic language, L, and we given a logic language, we consider the set of interpretations that give meaning to this set of formulas. So in order to, we can reuse the definitions of the previous presentations, and we can assume that, for example, in the presentation, we take into account a propositional logic, and set of words in this case would be just set all the interpretations of define the logic language, propositional logic language. And in possibilistic logic, since it's defined based on the notions of possibility theory, this is a counterpart. It's another theory that models uncertainty. Then we define a possibility distribution that associates to each element of this set of words, is an interpretation, a value that varies between 0 and 1, where the more this value is close to 1, and the more this interpretation is considered to be possible. Together with the possibility distribution, we define a possibility measure and a necessity measure that define respectively a possibility value and a necessity value of a formula in the classical logic language. So for a possibility measure defines just the higher possibility degree of an interpretation that satisfies that formula. And the necessity measure defines how certain that formula, according to our knowledge, according to the knowledge encoded in the possibility distribution, is necessary, is certain in this case. So, and is defined as 1, that is the highest possible value, minus the possibility of the negative formula. I think it's worth mentioning that there's a connection between these two measures and the notions of uncertain probabilities. More specifically, a possibility measure can be considered as upper bound of a family of probability measures, and the necessity measure can be considered as a lower bound. So a possibilistic formula can be defined as follows. So since it is a weighted logic, we have that the first member is a classical formula, and the second member is a value between 0 and 1 with 0 excluded. And we consider only possibilistic logic, also called necessity value possibilistic logic, because when we define constraints in this logic, we just specify the lower bound of the necessity degree of a formula. So the constraints in this logic just specify to what extent, what is the minimum value of the certainty degree of a formula. The more this value is close to 1, and the more this formula is considered to be necessary, more certain. If we have in our theory that all the formulas have value 1, then this coincides with classical logic. But if we want to express uncertainties of a certainty of truth value of a formulas, then we have this freedom in this logic of expressing something that is between 0 and 1, with 0 excluded. So here in possibilistic logic, we make a clear distinction between truth value of formulas and uncertainties over the truth values of formulas. So, and this is the important, one of the most important features of this logic. Before continuing the explanation of the learning settings, because the main goal of this presentation of this work was to study learnability of this logic. And but I think it's worth mentioning some modeling capability of this logic, just to let you understand why we chose this logic and why it's interesting in modeling uncertainty. So let's assume that there's a farmer that notices that there's a tree that is becoming sick, and this farmer would start identifying some causes that may be responsible for this sickness. So maybe too few fertilizer, or too much fertilizer has been given, or it may happen that some insects are responsible for this illness. If we try to model uncertainty of the farmer with a probability measure, we have that the more the first event is probable, and the less the second event becomes probable, because they are mutually exclusive events. And the other way around holds too in this case. But in case of complete uncertainty, we would like to have freedom in assigning uncertainty degrees that can be in some cases also fully possible. So in case of a complete uncertainty, the farmer may say, yeah, I don't know if too few or too much fertilizer or insects are responsible for these causes. But if I don't know anything, then all of them are fully possible. And then with additional information, some causes may be more possible than others. Or assume that we have, instead of having the complete uncertainty, we have additional information that is that alpha, so the first two causes may be more possible than the third cause, maybe because it's not the right season for insects to hatch. And we would like to have the possibility, have the freedom of assigning these values, no matter how the value of gamma, no matter of what the value of gamma is. For example, let's give 1/3 as the possibility of this event. If we again try to model this uncertainty scenario with possibility, with the probability measures, then we have that if we want to have alpha and beta with the same degree, uncertainty degree, then by Laplace criterion we are suggested to assign 1/3 to also the other two events. In this case, we lose information that we previously wanted to model. That is, that the first two events had a higher certainty degree than the third event. And once again, with possibilistic logic, we are free. So events or causes so the probabilities of events must not sum up to 1. So we are more free also in this case to assign any value alpha and beta that is greater to a third value gamma. Also, this uncertainty modeling capability plays nicely when we either don't know how many possible events there are, or when we start adding new events. Once again, if we try to model this with probability measures, and we are in case of complete uncertainty, then the more events we consider and the less probable each single event becomes. But yes, in some scenarios, we would like to have that everything is fully possible, no matter how many events, and even in case we don't know all the events, that can be the cause of, in this case, the sickness of the tree. Finally, we have also learning conditions where we have data that has contradictory information. Imagine that the farmer knows that someone says, I put fertilizers yesterday, and another farmer says, no, no one put fertilizers yesterday. We know that if we model this situation with classical logic, then we have a complete disaster. But in case with possibilistic logic, we actually can manage this inconsistent information, because possibilistic logic allows for partial inconsistency. Okay, so this concludes the part where we kind of justify why we are interested in learning the logic formally is called possibilistic logic. But in order to study learning learning phenomena and learning settings, we need to specify what is a learner, and what is the how the learner can acquire information. And we do that by using the mathematical formalizations offered by computational learning theory. We define we use the definitions of a learning model, specifically a learning model called exact learning, where the goal of the learner is to exactly identify an unknown target concept. In this case, so in these settings, the target concept is possibilistic logic theory, or consider in this case a set of possibilistic logic formulas. So the learner, we have in this model a learner that wants to identify the unknown target, and we have an oracle that knows the target that can answer queries to the learner. We are in this case of the active learning scenario, where the learner actively selects the queries, and the oracle has to answer those queries. We consider two different types of queries that the learner can ask. The first one is called a membership query, where the learner selects a possibilistic logic formula, and the oracle checks if the formula is entailed by the target. Now here, the learner says, is it true that P holds with certainty degree at least 0.3? The oracle would check if the target entails this formula, and it holds because the target says that P holds with certainty degree at least 0.4. So this means that it holds with certainty degrees at least 0.3. So the answer of the oracle would be yes, because the entailment check is satisfied. The second query, so otherwise, if the entailment check is not satisfied, then the answer of the oracle is no, a simple no. The second query is called an equivalence query. Here the learner sends its entire hypothesis, and the oracle checks if the target is equivalent to the hypothesis. If it is not equivalent, like in this case, then the oracle has to send a counterexample. That is a formula that is not entailed by the target and entailed by the hypothesis, like this possibilistic logic formula, or the other way around, a formula that is entailed by the target and not entailed by the hypothesis. Then with this information, then the learner will refine his hypothesis and continue with the learning phase. At some point, then the learner will hopefully send a hypothesis that is equivalent to the target, and the oracle in this case would just say yes, they are equivalent. And this signals the learner that the learning phase is finished, and the learner will output the hypothesis. So this is how we studied. So we studied the learnability of possibilistic logic settings in this way. So by using this notion. And here I would like to show you the results. So we divided our study in different parts. We asked ourselves, what if the learner is allowed to ask only membership queries? What if it is allowed to ask only equivalence queries, or both membership and equivalence queries? Then we also divided the study in two parts. The first one, in which we assume that the learner knows the precision of the digits needed to express any possible necessity degree present in the target. Also when the precision is not known. So this information is not known. And the learner has also to learn all the precision, the least amount of digits that are needed to represent every valuation of necessity degrees in the target. We have three different columns with three different colors, and each color is associated to a specific question. Yellow column, we try to answer the question, is the possibilistic logic framework learnable? So we wanted to, so in this scenario, we do not take into account the time needed for the learner to compute hypothesis, or the number of queries needed to acquire information and form the hypothesis that is equivalent to the target. We just want to know, if we have a limited amount of resources and a limited amount of time, do we actually learn can we actually learn a hypothesis equivalent to the target? Turns out that this is always the case. When we have equivalence queries, then we can learn easily the hypothesis by increasing the length of the hypothesis. And we can do iteratively until the hypothesis that the right length of the hypothesis is identified. And yes, by just listing to all through hypotheses, then we are able to identify the target. In the second column, we ask ourselves if it is possible to transfer polynomial time learnability results from classical logic to the possibilistic extension. Here, in this case, we take into account time constraints and the number of queries that the learner has to ask to the oracle. And in this green column, we answer the opposite question. So if polynomial time learnability results from possibilistic logic is transferable to the respective classical setting. When we have these check marks, then the answer of this question is yes. And when we have the only negative result is when we have membership queries and when the precision is not known. But so in this case, we have that this is not as surprising, because it's just like identifying a number in an interval of infinite numbers. And I will give you some details soon. By using reliability results present in literature, we are also able to transfer our positive results into the probably approximately correct learning model, where the goal of the learner is not to exactly identify a target, but to find a target that is just an approximation, an hypothesis that is that with the low probability misclassifies an example, a formula. So just to give you an idea of how we can prove non-learnability in this scenario, assume that the target has only one formula, and the goal of the learner is to identify the evaluation of that formula, the certainty degree. And this value, so the value can be between 0 and 1. And the learner can ask a membership query. And if the answer to the membership query is yes, then this interval will be bound, with the lower part of the interval will be bound. If the answer of the membership query is no, then there will be a bound on the larger values of this interval. But you have you can notice here that no matter how many queries we ask, we always have an interval, and this interval has infinitely many values. So the search space of the hypothesis will always remain infinite. So this alpha can be 0.311, or can be 0.31111, and so on. So the learner will never know when it has to stop and find the hypothesis. In order to prove transferability results, we assume that there's an algorithm that runs in polynomial time, and this algorithm will ask queries. We provide an explanation of how we can translate those queries into queries that the current oracle taken into consideration can understand. And then we explain also how we can translate the answer that the oracle that we have. We can translate those answers to answer the original the classical algorithm. In this case, we want to transfer learnability results from classical to possibilistic can answer. And the idea is that by running many times polynomial time algorithm, we are able to form a hypothesis that is equivalent to the target in the other setting. Yes, so I conclude the presentation, and thank you for your attention. The take-home message this presentation, I hope it's been clear. So we want to find a logic that is able to model phase of uncertainty, especially when there's a very high degree of uncertainty. Also able to model cases which we have contradictory information. And then once we identify this logic, we wanted to study the learnability properties. And these are the results of our study. One last thing is worth mentioning is that when we have polynomial time, so when we have transferability results in the equivalence query, this is not in the most general case, but we need to have additional assumption on, for example, the learning algorithm. But yes, for the interset readers, we can also have additional discussion. Okay, thank you.